Good morning, students. I hope you are all okay. Yesterday, in the last class, we have discussed about how to design a Glantry Girder. We have shown, we saw that what is the Glantry Girder, how a Glantry Girder operates, what is the operating mechanism, what are the basic types of a Glantry Girder. Then we discussed about how the design procedure occurs for a Glantry Girder, how the loads are calculated. As you know, the Glantry Girder operates in a wheel load, so how to calculate the wheel loads, then how to determine the wheel load on the crane, then how to determine the maximum bending moment and the shear force due to this wheel load. Finally, we have designed the Glantry Girder with the bending moment and shear force, then did all the necessary checks. We learned about that. So today we will be applying the design procedure because we will be designing a Glantry Girder problem. Okay, so let us start our lecture by starting the Glantry Girder problem. Okay, so our problem states that, 1 minute, design a Glantry Girder to be used in an industrial building carrying a manually operated overhead traveling crane. Crane capacity is given, self weight of the crane girder excluding trolley given, self weight of the trolley given, approximate minimum approach. I think you know what is a minimum approach and what is the requirement of that, so that is also given. Wheel base, that is given. Center to center distance between the Glantry Girder is given. Center to center distance between the column is given. Self weight of the rail section is given, and diameter of the crane wheel is given. The steel grade is AP410. Design also the fielded, so the design of the connection is also required. So let us design that. Okay, so determination of the first step is the determination of the wheel load, that we think it is here, the determination of the maximum wheel load. So you think that you see the wheel load that is coming to the each wheel, 1 wheel, 2 wheel, 3 wheel. So each wheel will be having combination of these 3 load: vertical load, lateral load and longitudinal load. But first, the bending moment and the shear force that will be actually acting is due to the vertical load. So first we will determine the vertical load. How to determine the vertical load, we will see that now. So let us see what is the meaning of the vertical load. Let us come to the load diagram. So here you can see the point load is acting here. The point load is due to the crab weight plus the concentrated load on the crane. That means the weight of the crab we have to consider plus the concentrated load on the crane we have to consider. So weight of the crab, that means the self weight of the crab. So self weight of the crab is given, that is equals to crane self weight of the trolley, that is 40 kilonewton, and concentrated load on the crane means crane capacity. So how much capacity the crane can take, it is given as 200 kilonewton. So total concentrated load 200 plus 40 kilonewton, the 240 kilonewton. This is the first load, that is the concentrated load. Let us change into factored load. The load will be factored. So what is the factor we have to take? So let us open the factored load page where it is, I think, load factor, no? Wait. So you see here in this diagram, it is dead load plus crane load. One second, let me download it first. In the picture, in the table number 4, there is the load factor gamma F that you see. So here the crane load is considering. So CL, that is the crane load. Okay, for crane load, CL, DL plus LL plus CL, the factor is 1.5. Now the load is acting as a dead load, so 1.5 factor we have to take as a load factor. So taking the load factor as 1.5, then this is the factored concentrated load. Now if we come again into this picture, so there is a UDL, uniformly distributed load. That uniformly distributed load is due to the position of the self weight of the crane girder. But in our math, the self weight of the crane girder is giving in 200 kilonewton, which is a concentrated load. So we have to distribute it evenly, uniformly over the total span of the crane girder. So let us find out first what is the span of the crane girder. So if you see in this picture, the span of the crane girder, that is distance between one rail to another rail. This is the rail, I think you know. So this is the one rail and this is another rail. So distance between Glantry rails is 16 meter. So the total uniformly distributed load over the crane girder, that will be equals to 200, that is the concentrated load, divided by the CC distance between the Glantry rails, that is equals to 12.5 kilonewton per meter. This is the self weight of the crane girder that is acting as a uniformly distributed load. So factored UDL, that will be equals to 18.75 kilonewton per meter. So we have got the value of these two load, point load and factored point load, and this is the uniformly distributed load over the actual span. So we have got the span value. So 360 kilonewton, the applied factored concentrated load is acting here, and 12.5 kilonewton per meter, that is the uniformly distributed load, that will be over 12.5 into 1.5 factored. So 18.75 factored load, that will be acting all throughout the member crane girder. Now that distance, so the maximum reaction force is achievable. The maximum reaction force is achievable when the crab and the crane arrangement, total arrangement, is at a distance C from the distance, minimum approach distance from the one of the support. It may be here or it may be here. I am taking it in that direction. So if it is here, so the minimum approach, it is given in the math, I think. The minimum approach, it is given approximate minimum approach of the crane 1.20 meter. So 1.20 meter is the minimum approach given. So we have found out what is the what is the best position, so that we can get the maximum reaction force on any wheel. So the maximum reaction force we are calculating first. So taking moment, so you know how to calculate the reaction force. You have done it in your solid mechanics in basic third semester. I am just remembering it. So taking moment at B position. So RA into total length 16 into that load into distance between that to that, 16 minus 1.2 plus 18.75, this is the UDL. So W into L by 2, that is W into L into L by 2. So RA we are getting 483 kilonewton, and similarly RB we are getting 177 kilonewton. Now, so we are getting maximum reaction at that position. So we will be taking the maximum reaction for that position. That position, the maximum reaction will be taken. So the maximum reaction force that will be coming to the wheel is that wheel. That means that girder we have to consider. Okay, if the girder is in, if the crab is in that position, then we have to would have to calculate that girder. So we have to calculate that girder. Now this load, if you see this picture again, in this picture you can see in a normal single crane girder, here it is a single crane girder, it is a single crane. Two wheels are generally specified for one end. For one end, two wheels is for one crane girder, and another phase there are two wheels. So two wheels, so that reaction force will be divided into two numbers of wheels. So maximum wheel on each wheel, that is 241.5 kilonewton. This is the maximum vertical load that is coming. Now coming to this part, as we have considered also, due to the sudden stopping or sudden braking, there will be some impact effect on the load of the load. It may be vertical, it may be horizontal, it may be lateral. As we are considering vertical, so we have to consider the impact effect for the maximum vertical load, considering that. So this is the chart that gives us the maximum load that is coming due to the maximum load that will be coming due to this impact effect. So if we consider the impact effect for EOT crane and MOT crane, EOT means electrically operated and MOT means mechanically operated. So for mechanically operated crane, now let us see in our question, the crane is industrial building can in a manually operated overhead. So manually operated crane means MOT crane. So for MOT crane, 10% of the maximum static wheel load we have to consider. So let us come to the point. So maximum static wheel load on each wheel, that is 241.5 on each wheel. So if we consider the additional impact allowance, that is 10%. So impact allowance for MOT we are taking 10%. So 10% of 241.5 we have to add that with that load as a impact allowance. So total load coming to one wheel, considering the considering the impact factor load, that is equal to 265.65 kilonewton. That we have got. So that is the load. So load determination concept is over. Now coming to the determination of the maximum bending moment. Step number 2 we are considering now, determination of the maximum bending moment. Now determination of the maximum bending moment. So maximum, as I think you have read all through all the notes, my materials, you can see there that the maximum bending moment in a crane wheel can only occur only when one wheel and the base, the CG of the wheel base is equidistant from the center of the Glantry Girder span. So this is the Glantry Girder span. It is the Glantry Girder span. That picture I have shown here. This is the Glantry Girder span. This is the center of the span. This is the center of the span. This is the center of the span. All right. This is the center of the span. This is the actual span of the Glantry Girder. Now we are determining the maximum bending moment for a Glantry Girder. So this is the Glantry Girder span center line. Now one wheel is placed here and the center line of the wheel base is placed here. It should be equidistant. Now only it will be possible, it is written here, only it will be possible that the CG of the wheel and the base and another wheel is placed at a B/4 distance from the center of the span. So it is placed at B/4 one wheel and another B/4 it is placed the center line of the load. So considering the picture, so this will be the now. Here it is written here that we also have to consider the sail point of the girder when calculating the bending moment. As we have considered the sail point of the crane girder when calculating the load, wheel load, here we have to also consider the sail point of the Glantry Girder. Now in our math, if we see, no sail point of the Glantry Girder is specified. So you have to assume that value. It is generally assumed between 1.5 to 2.2 kilonewton per meter. So let us take that value. So we are assuming the load to be 1.8. It is in between that. So we are taking 1.8 kilonewton per meter. Also sail point of the rail. So here the UDL is due to the sail point of the Glantry plus the rail. Rail means that rail is here. So rail weight has to be considered also. So sail point of the rail, it is given in the math. That is sail point of the rail that is given in the math. What is the value given? Sail point of the rail. Sail point of the rail. Sail point of the rail section 300 Newton per meter. It is the given. So it is an UDL. So let us so total load, total UDL load, that is a total uniformly distributed load over the Glantry Girder will be equal to 1800 plus 300 2100 Newton per meter. This is the UDL. Now we have to take it a factored load. So factored UDL, that will be acting equals to 3.15 kilonewton per meter. 3.15 kilonewton per meter. This is the factored UDL. So putting the value here. Okay. Now let us come to this picture again. So here one wheel, here one wheel. So if we are considering the C portion, so the load on each wheel equals to 265.65 kilonewton. So R1 and R2 in this picture, R1 and R2 will be R by 2, R by 2. That means total reaction is we have calculated. So reaction on each wheel we also have calculated. So putting the value here, that is 265.65, 265.65, we are putting the value. Now equate B/4. What is the value of the wheel base? That is given 3.5 meter. It is in the math that is given. The wheel base equals to 3.5 meter. The wheel base is given. So wheel base is given. So B/4 equals to 3.5 by 4, that is equal to 0.875. So you see that 0.875 is given here. This is the distance of center line to the 0.875, and the wheelbase, center line of the wheelbase is like here, it will be b by 4. I haven't shown it here because we do not need that. So the loads are placed in a similar formulation, similar diagram like that. Now we have to calculate to calculate the maximum bending moment, we have to determine the reaction forces. So let us find out the reaction forces, which is similar to that reaction forces we have found in the previous section. We have to consider all the loads, we have to consider the moments. So RC we are getting 0.14, and RD we are getting 336.36 kilonewton. So this is the two values of the reaction forces that we will get. Now depending on the reaction forces, we have to determine the maximum bending moment. Now from the bending moment concept, I think you have got a clear bending moment diagram concept. In a bending moment diagram concept, if it is like that, if it is UDL, if it is a point load here, then generally the maximum bending moment occurs at the center point of the concentrated load. It is generally occurs. Okay, so here there are two forces, two concentrated forces. So the maximum bending moment will occur just under any of these two wheel loads. So let us find out the bending moment at position E and F. So first the bending moment at E. So I think you know how to determine the bending moment at E and how to determine the bending moment at F. I have used that formula, this concept, to determine the bending moment at E. So the vector we are getting 678.86 and 462.495. So if we put the bending moment diagram like that, if this is one load, if this is another load, the value will come like it will be like that. Okay, so the maximum value of the bending moment we are getting at this position. Okay, so this will be the maximum bending moment. The value of maximum bending moment is equal to 678.86. that is the maximum value of the bending moment mz. We have calculated that with the concept. So maximum value of bending moment we have considered. Now coming to the step number 3, that is the determination of the maximum shear force. So how to determine the maximum shear force? Maximum shear force will be determined in a similar fashion. So for the shear force to be maximum, it is said that one of the wheel loads has to be present over one of the support, like that. I am taking the support to be one load to be placed here. I am taking the value to be here. So it may be here or it may be here. Okay, there is no general conception. It may be vice versa. So I am taking it as here. So this is the wheelbase that is given. So this is the UDL. So similarly we have to find out the reactions. Now when loads are here, you can always see at the reaction forces, or like that, at the reaction forces generally the shear force is maximum. So let us find out the shear force, reaction forces for this support. So RC, taking all the moments, similar formula, we are getting RC is equal to 128.82, and as the load is acting here, so the RD will be equals to 379.38. that is the value of this shear force. So maximum shear force we are getting 379.38. that is the value of the shear force. Okay, so this is the value of the shear force that will be acting. Okay, this is the value of the shear force that will be acting on the Glantry Girder. So we have find out the maximum bending moment and the maximum shear force. Now we can concentrate on find out the bending moment due to the lateral forces. Step number 4, the lateral bending moment we have to find out. Now the lateral load we have to find out. So if we again go to the loading fatigue load diagram, here it is said that the lateral load is lateral load that will be considered that we do not have the value of lateral load. Here in this math only the vertical loads are given, but no lateral loads are given here. So when we are considering the lateral loads can only be calculated. The lateral loads can only be calculated by using this fatigue factors, because the lateral load will act as a fatigue load, impact load, the lateral load, lateral thrust and braking load, both loads basically the lateral load will be acting as a impact load. So for lateral load and for mechanically operated crane, 5% weight of the crab and the weight lifted on the crane, that means 5% of the wheel load we have to consider. 5% of the wheel load. So let us come out with that thing, 5% of the wheel load. So in this picture, so 5% of the total wheel load you have to consider. So what is the value of the total wheel load that we have got? The total wheel load value is the maximum load. Wheel load is equal to total wheel load. We are getting 483 kilonewton. That is the maximum wheel load. Okay, 483 kilonewton. That is the maximum wheel load. Okay. So that is not the maximum. So maximum load, maximum wheel load that is coming is, that one, 360 kilonewton is the maximum concentrated load due to the wheel load. Wheel load is the concentrated load. Maximum, what is said that the weight of the crab and the weight lifted on the crane, because only the load of the crab and the crane we have to consider. So only the load of the crab and the crane means only the self weight. So 360 kilonewton is the self weight of the total concentrated force. So that load is, 5% of that load 5% of the total wheel load equals to 5% of 360 is equal to 18 kilonewton. 18 kilonewton that we have got, 5%, because 360 is the factored load. We have calculated the load as a factored load. Okay, now forces on each wheel, in each wheel, what is the force? So now if the maximum force, let us see this picture. This reaction, the concentrated force is acting on all 4 wheels. So the lateral force coming to one wheel will be that load divided by 4, that is equal to 4.5 kilonewton. That is the total load coming to one wheel, 4.5 kilonewton. So we have got the value of the one wheel load. So let us go to that picture. So the maximum bending moment, how to determine that? Total bending moment on the girder by the proportioning. I have told you what is proportioning. Maximum total bending moment on the girder, because total wheel load on each wheel. Putting all the values here, 678.86 divided by 241. Here will be one mistake. It will be 265.65, and it will be also 265.65. These two are the values that we have to consider. So this is the value 265.65 and 265.65. This is the two values. So getting the value is equal to 12.65 and 7.07. There may be a wrong calculation. So please, if you do the math by yourself, please correct the calculation. Okay. So shear force, similar formula, total shear force on the girder by total wheel load on each wheel, that we have got 265.65. That we have got 265.65 divided into 4.5. Factored lateral force on each wheel, that we have got 4.5. So getting all the value 7.07, 12.65. This is the value of the actual wheel load, the actual bending moment and shear force due to the lateral force that we have calculated. Now coming to the step 5, that is the important, because we are now starting the design. Trial plastic section modulus is calculated, putting all the values here. We know the MZ, we know all the things, 3937.388. Now economical depth and economical width of the girder, that we have to find out by these two formula, L by 12 and that. So L by 12 we are getting 666.67 and L by 35 we are getting 228.57. Now let us open IS SP6. Let us open IS SP6. If we see the I section, with highest depth here, if we see the I section with highest depth, we can see ISWB 600. That is the only section that can be provided. This is the highest I section specified by the Indian Standard Code. So ISWB, but it has ISWB 600. That means 600 is the maximum, but we have to provide more depth of the girder. For that we are taking one channel also. The channel we are taking is equal to ISMC 300. These two are we are taking. ISMC 300 we are taking. ISWB 600 and ISMC 300. That value we are taking. So one is ISWB 600, another one is ISMC 300. So writing all the properties here, I think you can get all the properties from this IS SP6 or IS 800 at the last pages in your code. You can see the plastic section modulus. For that, all the sections are also given there. So I have written all the values there. CYY, center of gravity, it will be also required for the channel section only, so I have written that also. So let us draw the section. So this is the actual Glantry Girder section that we have got. This is the actual Glantry Girder section, that is the total section, that is the 300 is the total depth. Now here the channel section is placed in a upright down position over the I section. So this is the total channel section. It is placed here. Okay, so this is the depth, total depth of the channel section that we have got 300 mm. Okay, so 300 mm. So we are finally getting the value. Okay, so this is the total Glantry Girder section we have got. Now coming to the next step. Then step number 6 we have to consider. Then we have to determine the sectional property of the built-up section. IXX, IYY, ZPZ, ZEZ, ZEY and CG of the built-up section. As is the built-up section, the CG will change basically. Let us find out the CG. Find out first CG of the whole section. How to find out the CG? You know, I think A1Y1 plus A2Y2 divided by A1 plus A2. A1 means the area of the, first the area of the channel section. Area of the channel section, area of the channel. So channel section area we have got, it is 4564. Putting the value here. Y1 means, what is the meaning of Y1? Y1 means the distance from the CG of the section to the CG of the whole section. Let us take the CG of the CG of the A1 Y1. Y1 means the CG of the I section, CG of the channel section. CG of the channel section is 23.6. Written the value here. Similarly, the CG of the taking moment of the area at the top of the fiber. So we are determining the neutral axis base at that portion. So for the channel section, the Y1 means that distance, and for the I section, Y1 means from here to the center of the I section. So center of the I section means the depth of the I, the half of the depth of the I, 300 from here to here, plus that thickness of the wave of the channel section. Thickness of the wave is equal to 7.6. So putting all the values here, getting a 251.37 from the top of the fiber. From the top of the fiber is equal to 251.37. So from the bottom of the fiber it will be equal to 600 plus 3. We will determine the value in the later portion. Now IZZ of the total section using parallel axis theorem. Now get it very carefully. Get it very carefully. Now when we are determining the IZZ, consider this is the I section, this is the channel section, this is the Z axis of I, this is the Y axis of Y, this is the Z axis of channel, this is the Y axis of channel. Now when we are determining the IZZ of the total section, now if we turn it like that, here we are placing it like that, so this now become the Y section, Z axis, and this now becoming the Y axis. So when we are calculating the IZZ of the total section, the IZ of the I section, but the IY of the channel section has to be considered. Very much carefully listen, because this is the main part. IY of the channel section will be considered because IY pass through the Z axis. The IY of the channel, the Y axis of the channel in this picture is now becoming the IZ. Similarly, Z axis of the channel is now becoming the Y axis of the channel. So when we are determining, I have written that here also, to calculate the IZZ, the total section of the IY of the channel section will be used, and when IYY, the total section calculated, the IZ of the channel section will be considered because of that funda. Okay, very much listen, very much understand, very much carefully. So IZZ of the total section, that is equals to, formula is equal to the, this is the parallel axis theorem. Now, so IZZ is equal to IZZ of the I section plus AH bar square, IY of the channel section, that is the main thing, plus AH bar square. So H bar means the distance between the CG and the CG of the whole section and the CG of the section. So when we are determining the IZ, so IY CG will be used, that distance will be used for channel section. Putting all the values here, we are getting the IZZ of the total section, that value. Now, when we are calculating the IYY of the total section, you see the IYY pass through the actual y-axis. So there will be no need to determine the y-section IYY with the help of parallel axis theorem. So determining the parallel on total section IY of the total section, here I have written that also for your clarification, IY of the I section and IZ will be of the channel section. So putting all the value here, we are getting that value. So IYY and IZZ is determined. Now coming to the most important and most interesting part, ZPZ of the whole section. First, let us remind you ZZ, how to calculate ZZ, ZPZ. What is the meaning of ZPZ? If this is a rectangle section, this is, first we have to find out the equal area axis, we have to find out. Then for the portion above the equal area axis, we have to find out the CG, and for the portion below the equal area axis, we have to find out the CG. Then the distance between the CG and the equal area axis, that is y1, and this is y2. That two we have to consider, y1 and y2, and consider a1 is the area of that part and a2 is the area of that part. So what is the formula for ZPZ? ZPZ, that is equals to A by 2, that means A1 plus A2, Y1 plus Y2. This is the formula for calculation of the ZPZ. We will use that. I think you have a clear conception about that. I have done it in your plastic analysis in your class. So let us go for that here. So first let us find the equal area axis. We have found the equal area axis. So equal area axis, consider the equal area axis at a y dash from the bottom. From the bottom we are finding out. So for that area, so as this is the equal area axis we are assuming, so that area will have half of the total area. That area will have the half of the total area. So as we are finding the equal area axis, so that area will have half of the total area. So total area, that is equal to total area of the I section plus area of the channel section divided by 2 into, so that portion into the CG from that to that, and that portion CG from that to that. So total area of that plus area of that portion equals to that value. We are getting y dash equals to 525.83 meter from the bottom fiber. So y dash will be equals to 81.77 meter top fiber. 81 from here to here, it is 81.77. So the equal area axis have been found out. So I want to clarify one thing, that the calculation I have done here with the help of my mobile, so there may be some mistakes in the calculation. Please correct it and then do the math. Now the distance of the CG of the area, above the equal area axis, we have to find out. Y1 dash we have to find out. So first finding out the y1 dash. I think you know how to find out the y1 dash. There is a CG distance for only that area. So finding out the CG distance of that area. Similarly 58.864 I have got. You may got another value. Similarly distance of the CG of the area below the equal area axis. Similarly using the formula, that is only for that portion. So area into from moment to here plus area from moment. So I think you know how to find out the y2 dash. I have shown it in the previous section also. So we are getting 382.28. It is the two values of the y1 dash plus y2 dash. So the ZPZ of the total section, if we use the formula a by 2 into y1 dash plus y2 dash, this is the total area. So 5081.603 into 10 to the power 3 in millimeter cube. That is the actual ZPZ of the total section we have found out. Similarly, ZPZ we have found out. Now let us open again. What is the meaning of? What is the meaning? All right. What is the meaning of ZE? ZE means if it is a rectangular section, consider rectangular with B and D. So ZEZ means BD cube by 12. This is the moment of inertia of the total section divided by D by 2. Okay, D by 2. I think this is the formula. So let us see there IZZ of the total section, as we are finding ZEZ, IZ of the total section divided by the y double dash. Y double dash means I have shown you distance of the CG of the total section from the extreme fiber of the section. Now let us go in that picture again. If this is the, okay, let us erase some of that. Now if this is the CG, what is the extreme fiber from the CG? That or that? I think that is the extreme fiber of the CG. So from CG to the extreme fiber distance is 356.23. So putting the value here 356.23, we have calculated the value. Total section minus the CG distance from the top, we are getting the 356.23 value. I have shown it there also. So ZEZ, we are getting that value. Similarly ZEY. Now when we are calculating the ZEY, what is the y section equal y section y axis? This is the y axis CG. What is the extreme fiber? It may be that, it may be that, any of that. Let us erase some of that. Okay, now it will be clear. So this is the actual y CG of the in the y section. So this is the maximum fiber. So from here to here, this is the distance of the maximum extreme fiber, or this is the distance from the extreme fiber. It is generally 300 by 2. 300 by 2. So putting the value here 300 by 2, we are getting 300 by 2, that is 150. We are getting the value of the ZEY. So all the values have been calculated. We do not know, we do not require ZPY. Okay, we will not be requiring it in our maths. We are not determining it. Okay, now coming to the section classification. Section classification we have to determine for both the sections. It may be I, it may be channel. So first for the I section, the section. So it is determined as per table number 2. So let us go for table number 2 here. I think the table number 2 is in the upright position. Okay, this is the table number 2, I think. Okay. So when we are calculating the I section, first B by TF. Okay, zoom in little bit. B by TF and B by TF and D by TW. Okay, this have to find out. So B by TF, B means for a I section, B means from here extreme fiber to the center, and from the channel, this is the depth of the flange. So putting all the values, B is equal to, for channel, for I section, B is equal to 250 by 2 T, and D is equal to, D means from here to here. So from here to here you have to minus the width of the flange, thickness of the flange, and the root radius. So the root radius we have determined here, that is for channel R1 18 mm. So putting the value here, we are getting 516.8 D. So D by TW we are getting 43.8 and B by TF 5.3 for the I section. And here the age means here also. So age equals to, okay, 39.47. Here the calculation has also a wrong calculation has been done. Here also the same thing has to be determined. 300 minus thickness of the flange, TF is equal to, I think TF value is equal to 13 plus thickness of the flange equals to 13.6. so here these two values also has to be incorporated. It is my mistake. 13.6 plus 13, these two values has also to be incorporated here. 13. Okay, so getting the value will be changed here, so we are getting a plastic section. So it is now coming to the 8 point. So welded and rolled, it is always 9 point, it should be less than 9.4 epsilon or 8.4 epsilon, the B by TF value, and D by TW 84 epsilon. So as we are getting these two values, so it is a plastic section. Now coming for the moment capacity, I think the moment capacity section we are entering now. So now we are determining the moment capacity. So moment capacity formula, let us come to the design procedure. For the moment capacity, beta mdz is equal to 8.2.1.2 beta b zpz fy gamma m0. Let us come to 8.2.1.2 clause. 8.2.1.2 clause says that, where it is 8.2.1.2. okay, 8.2, 8.2, I think it is here. Okay, the 8.2.1.2 clause says that when the factored design force does not exceed 0.6 Vd, where Vd is the design shear strength of the cross section, the design bending strength MD. Now we are using that formula beta b zpz gamma fy by gamma m0 only because we are assuming that the shear force that will be determining in the next steps will be less than the design shear, will be 0.6 times Vg, that is the design shear force we will determine, will be more than the shear force in the section. We are designing based on that concept, because the Glantry Girder is a member where huge amount of load is coming. So always we will try to keep the section is a low shear case. If it is not, then we have to change the section accordingly. Okay, so let us take this formula and determine. So let us come to the formula. So beta b we know, the beta b is 1.0 for plastic and compact. Beta b we know. Putting all the values here, we are getting 1154.91 kilonewton meter, which is also less than 1113, that is 1.2 ZEZ Fy by gamma m0. Now it is also mz dz greater than mz, so the moment capacity is same. Now mdyf we have to also determine, where mdyf means beta b zpyf. So zpyf, what is the meaning of zpyf? zpyf is the plastic section modulus of compression flange about y axis. Plastic section modulus of the compression flange about y axis. That means the plastic section modulus to determine. So I have shown you in the previous class how to determine the plastic section modulus for the compression flange only. So when we are determining the plastic section modulus for the compression flange, we will use that formula. So putting all the values here, putting all the formulas here, this formula you are using. Okay, this formula you are using, putting all the value, we are getting 719.171 into 10 to the 3 new millimeter cube. Putting the value here, beta b we know, Fy we know, ZEY we have calculated the value of the ZEY here. If you remember, ZEY I have calculated, that is 777.39. So putting the values here, we are getting 163.45. So 212.015 kilonewton. So it is also less. So hence it is okay. So all the criteria have been fulfilled. Now coming to step number 9. What does it say? It says combined local capacity check. Combined local capacity should be checked by this formula, where mz is the maximum bending moment that we have got. What is the value of the maximum, and mdyf is equal to the maximum bending moment due to lateral load. So let us come to the formula where we have calculated. So maximum bending moment we have got is 678.86, and maximum bending moment due to the lateral force we have got is 12.65. So let us put all the values, and we have also determining mdz and mdz we have calculated, that is 1154.91, and mdyf we have calculated 163.45. Putting all the value, we are getting it is also less than 1.0. So it is also under the limit. So local capacity is safe for the design. Coming to the check for the buckling resistance. This check, after check number 10, check number 10 is that not much necessary, because if you have the time in your, I have told you in the previous class that if you have your time in the exam, then you can proceed for the check. Let us do the check anyhow. So mdz will be calculated 8.2.2. I think you know how to determine the, because it is the laterally unsupported beams, we have to check it for that also. So for the laterally unsupported beams, that formula we have to use beta B, ZP, FBD. So beta B we know, ZPZ we have determined. Now coming to the FBD. For FBD we have to use all. For FBD we have to use all these cases. All these cases we have to determine the MCR from that formula. Now that formula won't be used because MCR it is for the two wheel loads. So for our cases the MCR will be used is that formula. MCR, where it is MCR, that formula will be used. C1 is equal to 1.046 for two wheel loads. Here two wheels are here, so putting all the values here, we are getting the value Ry is equal to Iy by A. We know all the things. Aj is equal to height of the flange. We know height of the flange means center to center distance between the two flanges. So here it is one flange, here it is the I section, from here to here. This is the distance of the, so total distance minus 7.6 by 2, 7.6 by 2. So getting all the values here, AJ we have determined, TF we know all the values. We are putting now. TF means thickness of the flange of I section plus flange of channel, wave of channel section. So using all the values we are getting 31.2. Putting all the values here, all the values 0.91, 900.16 is the value of the MDZ we are getting. MDZ we are getting 900.16. Okay, 900.16 is the value of the MDZ we are getting. So MDZ is also greater than the value of the MZ. Okay. So let us find out the so similarly MDY equals to, from that formula, ZYT into Fy by gamma M0. So ZYT is equal to, so on another thing it will be changed here. Now Iz of the I section that we have no Iz, but for channel section it will be Iy. So here is another thing it will be changed. So please make that correction in your previous note, and it will be dy4. Okay, Iy of the channel plus 2 I half into Iz of the I section. Please make that correction in your previous note. Okay, it is very much required. So putting all the value here, so Iy of the channel that we have got here, Iy of the channel equals to, if you see, so Iy of the channel is equal to Iz of the channel equals to 6362.6, and Iy of the channel is equal to 5298.3. So putting all the values here, okay, putting all the values here, we are getting where it is. Okay. So putting all the values 6362.6 and 5398.3.4 into 2. Putting all the values here on thing. All right. One thing, Iz of the channel it will be same, and Iy of the channel, because we are determining the Y section, so it will be Iy of the channel. Iz, because that Y section, Iz pass through the Y section of the channel that I have told you in the earlier section, so it will be Iz of the channel and Iy of the I section by 2. That is the value, because it is the half value. So putting the value here, we are getting 604.12. So putting all the value, we are getting 133.7. Now then comes the similarly combined local capacity check. You are getting the value combined local capacity check. The value is MZ by MDZ. You know MZ by MZ's value. We are getting 0.85. It is also less than 1.0. Hence this local capacity for the unsupported beam is also complete. Now coming to the shear capacity check. Very much important, because here we will know that if this is a low shear or a high shear case. So first VD we have to find out by Vn by gamma M0. Vn is equal to AV Fy W by root 3. AV means H into TW, because hot rolled section. Both channel and the I section both are hot rolled. So hot rolled section we are taking H into TW. H means height of the H means putting the value here, height of the I section, and T means TW is the wave thickness of the I section. Putting the value here into 250 by root 3, we are getting 929.01, which is much more greater than 379. So the shear is safe. Now let us check if it is a low shear case or not. So 0.6 into Vg we are getting 557.41, which is also greater than the Vz, that value. So here that is a low shear case. So the assumption we have taken from the calculation of the moment capacity, that assumption is correct. Then we can proceed from the next part. If the assumption is wrong here that we have taken, we have to change it we have to change the section first. Okay, so please make it very much clear, the shear capacity. Now coming to the check for the wave buckling case. So check for the step number 13, check for the wave buckling. Now FW is equal to B1 plus N2 plus TW into FCD. So B1 is equal to the strip bearing length that we know. Strip bearing length means dia of the wheel load that I have told you, diameter of the crane wheel. So in our math, the diameter of the crane wheel is given as 150 mm. So we will use that value here. Diameter of the crane wheel, we are taking 150 mm. Okay, diameter of the crane wheel 150 mm, and N2 equals to putting the value here h by 2 into 2 into TW. TW here, that here the TW will be the thickness of the wave thickness. Okay, so putting all the values here. So lambda W we are getting now. Lambda W we have to determine 2.45 D1 by TW. Similarly, the value we are assuming now the lambda W we have to calculate for the wave. Okay, because this is wave slenderness ratio. The wave means the wave of the I section. So I section TW is taken here. Putting the value of lambda W. Now we have got the slenderness ratio. Now for the slenderness ratio, that value, Fi that value, and class C. Class C means now this is I think the table number. So table number 9C for that case. So table number 9C. Let us go to table number 9C. Okay, table number 9C I think. Okay, for lambda W 107, that means 107 means 100 to 110. So that line and that line. So for 250, so these two are the values. So the value will be in between that. If you do the interpolation, I haven't done it. I have done it in my mobile. So if you can do that, you can see the value is coming 97.948 Newton per millimeter square. So the value of the FW we are getting. So value of FCD we are getting that. So value of the FCD, that is equals to FCD. Okay, the value of the FCD we are getting. So FW we are putting all the values. We are getting 346.3. Now that in our previous lecture also in these notes, please make it clear that the value of the FW, it should be more than the maximum wheel load on each wheel, because the buckling will occur due to the maximum wheel load on each wheel. Maximum wheel load on each wheel. Okay, maximum wheel load on each wheel. Please make it clear. Okay, maximum wheel load for the each wheel. So there is more than that, so hence it is okay. Bearing here, so check for deflection now coming. WL cube by that. So W is the total wheel load on each wheel, 241.5. A is equal to, we know, L by L minus B. B is the wheel base. Putting all the values. I is equal to IZ, maximum gross moment of inertia of the wheel built up member. Maximum, so maximum is IZ and IY, which is the maximum. IZ is the maximum. You can see also. IZ we are taking. So lambda cal, that is the delta cal, we are calculating 13.366. Now, if we are see that the deflection, maximum value of the deflection that we will take, that is where cranes are manually operated, L by 500. That means L means the span of the Glantry Girder. So putting the value here 800 by 16. So it is less than that. It is delta cal less than 16. So deflection check is successful. Coming to the last portion, that is the design of the connection. First, the shear capacity. Shear capacity is that Q is equal to V into A into Y bar divided by IZ. We know the V, maximum shear force, we have calculated 379.38 into 10 cube. We have calculated the value of the maximum shear force on the girder, 456. That is the value of the area of the, now IZ is equal to the IZ gross section of the total section. We are putting the value of the IZ here, total section, and A, this is the only area of the channel. Why? Because the channel need to be connected with the eye. Okay, so the strength of the channel we have to find out. So channel, the shear capacity, when we are determining the shear capacity, the channel section we have to consider. So the area of the channel we have used here, and Y dash is equal to the distance between the CG of the total section and the CG of the channel section. So the CG of the total section is from the top, it is 251.37 that we know. And CG of the channel section from the top is CYY. We have know that 23.6. Putting the value here, we are getting 271.13. Now let us find out the strength of the weld per meter run. So let us provide a 5 mm weld. We are providing a 5 mm weld. Okay, TT is equal to 0.7 into 5, 3.5. Strength of the weld. So TT is the throat thickness we have find out. So strength of the weld per millimeter run is equal to that value. So providing site welding, as the connection to be done is in the site, because in the shop we do not know what will be the channel, what will be the shape, and we cannot bring out the whole section all through from the site, from the shop to the site. So here site welding we are using, site welding. So putting it is much more than the strength. So the strength criteria is also okay. So all the criteria are getting fulfilled. That means the design is safe and sound. We have completed the design of the welded Glantry Girder. So all the criteria are satisfied, all the checks are done. This is the math that we have to do in your exam if it comes. So please be ready to do that math. Some of the steps, design of the connection, if it is not specified, you do not have to do that. Design of the reflection, you can skip. Buckling check, that means that check. This check, that means the check for the shear or check for the wave buckling, that check you can also skip. But other step you have to do. This is a very lengthy math. So if you are doing the math in your exam, please do it after much more practice, because practice is much more needed. Okay, so this is the math that you can final math of Glantry Girder. Up to that, the steel design syllabus is complete. So I have completed the steel design syllabus. Now in the calculation of this math, there may be some calculation mistakes because I have done it with my mobile. So please do the math by yourself and see if there is any calculation mistake, and please correct the mistake by yourself and do the math by yourself. Okay, so this is a very important and very interesting math. Please follow the math, please do the math by yourself. Okay, stay home, stay safe in this situation. Okay, and please study for your exam. Okay, thank you very much. Thank you for your class, and thank you for listening me for throughout the selection, throughout the semester for this steel class. Okay, thank you class, thank you very much.